Welcome to this explainer. Today, we are popping the hood to unravel the absolute mechanical magic of how your car actually works. I'm really excited to dive into this with you because the physics of how a vehicle speeds up, from the classic gearboxes we all grew up with to modern electric vehicles, is just endlessly fascinating. So let's jump straight into the core mystery here. Why on earth does a gas-powered car rely on the constant mechanical clunk of shifting gears, while an electric vehicle just seamlessly rockets forward without them? If you've ever driven both, you know exactly what I'm talking about. The feeling of accelerating is just radically different. To really grasp why they feel so different, we have to start with this idea. Gears are the logic of motion made physical. I absolutely love that framing. It reminds us that effortlessly launching a 2-ton chunk of metal down the road comes down to some really beautiful physical logic. We're not just talking about hunks of spinning steel. We're talking about energy transformers. Section 1. The magic of gears. Now, the real secret sauce of this mechanical magic is the gear ratio. This is the defining mathematical rule that dictates exactly how gears are going to behave, and it boils down to a super strict trade-off in physics. Basically, you are always trading speed for torque or torque for speed. There's just no way around it. You can't get something for nothing. Calculating this ratio is honestly a breeze. Say you have a 60-tooth gear being driven by a little 20-tooth motor pinion. You literally just divide them, and boom, you get a 3-to-1 ratio. So the output shaft is turning 3 times slower, sure, but because of that strict physical trade-off we just talked about, it's now turning with 3 times the twisting force. Section 2. Torque versus speed trade-off. Okay, so gears are energy transformers, but what are they actually doing down there? Well, they execute 3 main functions that completely dictate how your car moves. They change speed by increasing or decreasing the RPM. They amplify torque, which multiplies the output force. That's what gives you the push you need to accelerate. And they can change direction. That's what lets you back out of your driveway without having to somehow spin your engine in reverse. To put that into perspective, imagine a 5-to-1 gear reduction. It isn't just slowing things down a bit, it is giving you a massive 500% mechanical advantage in torque. And that right there is how a standard-sized motor manages to shove an incredibly heavy car right off the starting line. By sacrificing speed, you wildly amplify your pushing power. But of course, different problems require different gear geometries. Spur gears, for example, are highly efficient, almost 98%, but their straight teeth all smash together at once, which makes them super noisy. Helical gears, on the other hand, use angled teeth. They drop a tiny bit of efficiency, coming in around 96%, but they deliver the quiet, smooth power transfer that is absolutely crucial for passenger cars. You wouldn't want your daily commute sounding like a giant blender, right? Section 3. The gas engine problem. Now, armed with all that gear knowledge, we hit the central conflict of the traditional car. The gas engine has a really critical flaw. It only runs efficiently in a frustratingly narrow power band, typically between 600 and 7,000 RPM. Think about riding a bicycle. To get going from a dead stop, you need massive torque. But to fly down a hill, you need high speed. A gas engine on its own simply cannot do both. Section 4. Complex multi-speed solutions. So, to keep that limited engine in its happy zone, engineers had to get creative. Enter the planetary gear set. This thing is a total game changer. It's a rugged little system stuffed inside automatic transmissions with a sun gear, orbiting planet gears, and an outer ring gear. By using clutches to just hold different parts stationary, this single compact unit can miraculously spit out several completely different gear ratios. That means the transmission acts as the ultimate middleman. When you hit the gas at a red light, first gear kicks in with a high ratio, something like 3.5 to 1, multiplying torque to get all that heavy metal moving. But once you're cruising on the highway, it shifts into an overdrive ratio, maybe 0.8 to 1. Now the wheels are actually spinning faster than the engine, which saves gas and keeps your engine from literally tearing itself apart. Section 5. Why EVs break the rules. Now, here's where the whole paradigm gets flipped on its head. The contrast between these two systems is just staggering. A gas engine's narrow little limit is absolutely no match for an electric motor's massive functional range. We are talking about going from a ceiling of 7,000 RPM in a gas car all the way up to an incredible 20,000 RPM in an EV. And here is the electric vehicle plot twist. An EV generates maximum torque instantly from 0 RPM. That's why you get that crazy roller coaster launch feeling when you stomp on the pedal. Because it has this massive, highly efficient power band, it completely bypasses the need for those heavy, complex, friction-losing gearboxes. Instead, it relies on just one beautifully simple, single-speed reduction gear to handle everything from a dead stop to highway speeds. So as we trade over a century of heavy, multi-gear complexity for simple, single-speed efficiency, it leaves us with a pretty provocative question. If the very mechanics of how we move forward have fundamentally changed, what other unbreakable rules of the road are about to become completely obsolete? Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I'll catch you next time.